There is an assumption that nearly everyone makes, so fundamental and so deeply embedded in our thinking that most people never even recognize they are making it. This assumption shapes how we understand the world, how we interpret our experiences, how we imagine reality itself. The assumption is this: that physical objects possess definite properties at all times, whether we observe them or not. A chair has a definite position in your room even when you leave and close the door. The moon orbits the Earth with a definite trajectory whether anyone is watching or not. An electron in an atom has a definite location and a definite velocity, even if we have not measured these quantities. This seems so obvious, so self-evident, that questioning it appears absurd. And yet, quantum mechanics has taught us that this assumption, reasonable as it seems, is fundamentally incorrect when applied to the atomic world. Let me tell you how I came to recognize this assumption and understand why we must abandon it. When I was a young physicist in the early years of the 20th century, I absorbed this assumption without question, just as everyone did. It was woven into the fabric of classical physics, into Newton's laws and Maxwell's equations, into every successful theory we had developed. The entire edifice of classical physics rested on the idea that physical systems exist in definite states at all times, with all their properties having specific values whether we measure them or not. Our job as physicists, we thought, was to discover these properties and the laws governing how they change. When I began working on atomic structure in 1912, I initially tried to maintain this assumption. Ernest Rutherford had shown that atoms have a dense nucleus with electrons somehow arranged around it, and I attempted to understand how this system could be stable. My early atomic model proposed that electrons orbit the nucleus in certain allowed orbits, stationary states where they would not radiate energy despite being accelerated. I could still picture these electrons as little particles following definite paths, even though those paths were restricted to discrete orbits by quantum rules I could not fully justify. But even in this early model, cracks were appearing in the assumption. When an electron jumped from one orbit to another, emitting or absorbing light, what exactly happened during the transition? I could calculate the energy of the emitted photon. I could predict which transitions were possible. But I could not describe the electron's path during the jump because there was no path. The electron disappeared from one orbit and appeared in another instantaneously, without passing through the intervening space. Did the electron have a definite position during this transition? The question seemed to have no answer. As quantum mechanics developed through the 1920s, the inadequacy of the assumption became impossible to ignore. Erwin Schrödinger developed his wave equation, which describes quantum systems using a wave function rather than definite positions and velocities. The wave function is not a statement about where a particle is or how fast it is moving. It is a mathematical object that encodes probabilities for different possible outcomes if we were to measure these quantities. And crucially, the wave function can be a superposition of multiple states that would be mutually exclusive if they had definite values. Consider an electron described by a wave function that is spread out over a region of space. Does this electron have a definite position? According to quantum mechanics, no. The electron is not secretly located at some specific point with us simply being ignorant of where. Rather, the electron is genuinely in a superposition of being at many different locations simultaneously. Position is not a property that has a definite value until we perform a measurement. Before measurement, position is indefinite, existing only as a spectrum of possibilities with associated probabilities. This directly contradicts the assumption everyone makes. We want to say that even if we do not know where the electron is, it must be somewhere definite. But quantum mechanics says this is wrong. The electron is not somewhere definite before we measure its position. It is in a state where position simply does not have a single definite value. The property we call position does not exist in definite form until brought into existence by measurement. Werner Heisenberg, working with me in Copenhagen, crystallized this insight in his uncertainty principle. The principle states that position and momentum cannot both have definite values simultaneously. The more precisely one is defined, the less precisely the other can be defined. This is not a statement about measurement limitations or disturbances. It is a statement about what can exist. A quantum state cannot have both definite position and definite momentum at the same time because these properties are mathematically incompatible in quantum mechanics. The assumption everyone makes is that particles have definite values for all their properties at all times. Heisenberg's uncertainty principle shows this assumption is false. An electron cannot have both a definite position and a definite momentum. If we measure position precisely, forcing the electron into a state with well-defined position, we necessarily create a state with poorly defined momentum. Not because our measurement disturbed a pre-existing momentum value, but because a quantum state with definite position mathematically must be a superposition of many momentum values. I remember the long discussions Werner and I had about this, walking along the streets of Copenhagen late into the night, trying to understand what it meant to give up the assumption that properties exist independent of measurement. It was disorienting, almost vertigo-inducing, to recognize that we were not merely discovering new facts about atoms but were being forced to reconceptualize what we mean by physical properties and physical reality itself. The double-slit experiment illustrates the failure of this assumption with perfect clarity. When we send electrons one at a time through a barrier with two slits, each electron eventually hits a screen on the far side at a specific point. Over time, these impacts build up an interference pattern that can only be explained if each electron passes through both slits simultaneously, interfering with itself like a wave. Now, the assumption everyone makes would lead us to say that surely each electron really goes through one slit or the other, even if we do not observe which one. Perhaps we just lack the information to determine its path, but the path exists nonetheless. But this assumption is demonstrably false. If we place detectors at the slits to determine which path each electron takes, thereby forcing each electron to have a definite path, the interference pattern disappears. The very act of making the path definite changes the experimental outcome. Before we observe which slit the electron goes through, it does not have a definite path. It is not secretly going through the left slit or secretly going through the right slit with us being ignorant of which. It is in a superposition of both paths, and this superposition is what allows the interference. The path is not a property that exists independent of observation. It is brought into definite existence by the observation. This was profoundly troubling to many physicists, most notably Albert Einstein. Einstein felt that the assumption of definite properties independent of observation was essential for physics to be meaningful. He believed that physical reality must exist in a definite state whether we observe it or not, and that quantum mechanics, if it denied this, must be incomplete. We had many intense discussions about this over the years. Einstein would propose thought experiments designed to show that quantum mechanics led to contradictions if we took seriously the idea that properties do not exist independent of measurement. The most famous was the EPR paradox in 1935, where Einstein, Podolsky, and Rosen considered two particles in an entangled state. By measuring one particle, we can instantly know something about the other particle, even if they are far apart. Einstein argued that since we can choose which property to measure on the first particle, and thereby know that property of the second particle, the second particle must have had all these properties in definite form all along, waiting to be revealed. My response was that Einstein was smuggling in the very assumption that quantum mechanics requires us to abandon. He was assuming that the second particle has definite properties independent of measurement, but this is exactly what quantum mechanics denies. Before we measure the first particle, the entangled pair is in a superposition where neither particle individually has definite properties. When we measure one particle, we force the entire entangled system to collapse into a state where both particles have definite values for the measured property. But these values did not exist before the measurement. They were created by the measurement. Einstein never accepted this, and for decades the debate remained philosophical. But then John Bell developed a way to test experimentally whether Einstein's assumption was correct. Bell showed that if particles have definite properties independent of observation, as Einstein believed, then certain mathematical inequalities must be satisfied in the correlations between measurements on entangled particles. But if quantum mechanics is correct and properties do not exist until measured, these inequalities will be violated. Experiments testing Bell's inequalities have been performed many times with increasing precision, and they consistently confirm that the inequalities are violated. Nature behaves as quantum mechanics predicts. The assumption that particles have definite properties independent of observation is experimentally falsified. This is not philosophy or interpretation. This is empirical fact. What should we make of this? It means that the intuition we all have, the assumption we all make about physical reality having definite properties whether we observe them or not, is simply wrong when applied to quantum systems. This does not mean reality is subjective or that consciousness creates reality, or any such mystical notion. It means that reality at the quantum level has a fundamentally different structure than we imagine based on our experience with macroscopic objects. The properties of quantum systems are not pre-existing features waiting to be discovered. They are potentialities that become actualities through interaction and measurement. Before measurement, an electron does not have a definite position. It has a probability distribution for position, encoded in the wave function. Measurement brings a definite position into existence from these possibilities. The position after measurement is real and definite, but it was not there in definite form before the measurement. This is what I meant by complementarity, a concept I developed to help articulate the failure of the classical assumption. Different experimental arrangements revealed different complementary aspects of quantum systems, and these aspects cannot all exist in definite forms simultaneously. An electron has both wave properties and particle properties, but these are complementary aspects that require mutually exclusive experimental setups to observe. We cannot simultaneously see the electron as a wave and as a particle because these are not compatible properties that can both be definite at once. The assumption everyone makes is rooted in the law of non-contradiction from classical logic. A thing cannot be both A and not A at the same time. An electron cannot be both here and not here. It must have a definite location. But quantum mechanics shows that this classical logic does not apply to quantum properties. An electron can be in a superposition of being here and being there, which is neither definitely here nor definitely there nor somehow split between the two. It is a third state that has no classical analog, and trying to force it into classical categories by insisting it must really be one or the other leads to contradictions with experiment. Why do we make this assumption so automatically? Because our everyday experience involves only macroscopic objects where quantum effects are invisible. When we observe a chair, it appears to have a definite position whether we look at it or not. We can leave the room, come back, and find it in the same place. This is not an illusion. Macroscopic objects do behave classically for all practical purposes. But the reason is not that classical physics is fundamentally correct. It is that macroscopic objects are constantly interacting with their environment in ways that destroy quantum coherence. A chair is made of an enormous number of atoms, and these atoms are constantly colliding with air molecules, exchanging thermal radiation, and interacting with each other in complex ways. These interactions entangle the quantum state of the chair with the quantum states of environmental particles, spreading out the information about quantum phases into the environment in such a dispersed way that quantum interference effects become impossible to observe. What remains is classical behavior. The chair appears to have a definite position because quantum coherence has been destroyed by environmental interactions, not because it fundamentally has definite properties independent of interaction. This process, called decoherence, explains why the assumption works for everyday objects even though it fails for isolated quantum systems. Decoherence is so rapid and complete for macroscopic objects that we never see them in quantum superpositions. But at the atomic level, where systems can be better isolated from environmental disturbance, quantum coherence persists, and the failure of the classical assumption becomes manifest. The assumption everyone makes, that properties exist independent of observation, is therefore a kind of useful fiction that emerges from quantum mechanics in the limit where decoherence is strong and quantum effects average out. For macroscopic objects in normal environments, this assumption works perfectly well for practical purposes. But it is not fundamentally true. It is an approximation that breaks down when we study small, isolated quantum systems where decoherence is minimal. Recognizing this has profound philosophical implications. It means that the sharp distinction we draw between subject and object, between observer and observed, between knower and known, cannot be maintained at the quantum level in the same way as in classical physics. The properties we observe are not simply out there in the world waiting to be discovered. They are brought into definite existence through our interactions with quantum systems, through the process of measurement that forces superpositions to collapse into single outcomes. This does not mean that reality depends on human consciousness or that we create the world with our thoughts. The key is interaction, not consciousness. A photographic plate interacts with an electron and records its position whether any human ever looks at the photograph. But the interaction does change the quantum system, transforming it from a superposition to a definite state. The world is not arbitrary or subjective, but neither is it made of objects with all their properties defined independent of interaction. I have spent much of my career trying to help physicists and philosophers understand this, to see that the assumption everyone makes must be abandoned if we are to properly understand quantum mechanics. This has been difficult because the assumption seems so obvious, so necessary, so impossible to give up without falling into incoherence. But quantum mechanics shows us that we can give it up, that we must give it up, and that doing so leads to a coherent and empirically successful theory. The assumption that properties exist independent of observation is replaced in quantum mechanics by a more subtle picture. Quantum systems are described by wave functions that evolve deterministically according to Schrödinger's equation. These wave functions encode potentialities, probabilities for different possible measurement outcomes. When a measurement occurs, when the quantum system interacts with a classical measuring apparatus in a way that creates an irreversible record, the wave function collapses and one of the potentialities becomes actual. The property that is measured comes into definite existence through this process. Different properties are complementary and cannot all be definite simultaneously. Position and momentum are complementary. Different components of spin are complementary. Wave and particle aspects are complementary. The experimental arrangement determines which property becomes definite through measurement, and this choice necessarily leaves other complementary properties indefinite. This is not a complete theory in the sense that classical physics aspired to be complete. We cannot predict which specific outcome will occur in any individual quantum measurement, only the probabilities. There is genuine randomness at the quantum level, not determinable by any prior state or hidden variable. And we cannot eliminate the role of measurement, the interaction that brings definite properties into existence, because measurement is how we gain knowledge and how we do physics. Some physicists have tried to restore the assumption everyone makes by proposing alternative interpretations of quantum mechanics. The pilot wave theory of de Broglie and Bohm gives particles definite positions at all times, guided by a quantum wave. The many worlds interpretation says all possible measurement outcomes occur in different branches of reality. These interpretations are mathematically consistent with the predictions of quantum mechanics, but they seem to me to add unnecessary complications to avoid accepting what quantum mechanics is clearly telling us, that the assumption of properties existing independent of observation must be abandoned. Why cling to an assumption that is contradicted by experiment, that requires elaborate theoretical machinery to maintain, that does not help us make better predictions or design better experiments? Why not simply accept that quantum reality is structured differently than we imagined, that properties are potentialities brought into actuality by interaction, that the observer and observed cannot be completely separated? I think the difficulty is psychological and cultural. We have been trained by centuries of classical physics and by our entire evolutionary history to think in terms of definite objects with definite properties. This assumption is built into our language, our intuitions, our basic cognitive framework. Giving it up feels like losing our grip on reality, like descending into subjectivity or mysticism. But this is a false fear. Quantum mechanics is not subjective or mystical. It is rigorous, mathematical, and empirically verified to extraordinary precision. What we are giving up is not reality but a particular metaphysical picture of how reality is structured. We are learning that reality at the quantum level does not consist of objects with all their properties defined at all times. It consists of quantum states that evolve according to precise laws and that manifest definite properties through interaction and measurement. This is a different kind of reality, but it is no less real, no less objective, no less worthy of being called the truth about nature. The assumption everyone makes is that the world is made of things with definite properties that exist whether we observe them or not. Quantum mechanics shows us that this assumption, natural and intuitive as it seems, is an approximation that works for macroscopic objects but fails for quantum systems. Learning to think without this assumption, learning to accept complementarity and indefiniteness, and the creative role of measurement, is difficult but essential for truly understanding the quantum world. And in abandoning this assumption, we do not lose our ability to understand nature. We gain a deeper, more accurate understanding of how nature actually is at its most fundamental level.